Imagine discovering a hidden chapter in the story of our planet's dynamic past that could unlock the secrets to life on distant worlds. It's the kind of breakthrough that makes you wonder, what if Earth's lively geology isn't just luck, but a clue for finding habitable exoplanets? Scientists have just unveiled a fresh take on planetary tectonics that could transform how we view rocky planets' development, suggesting this episodic-squishy lid mode might be the bridge we've been missing. For beginners dipping their toes into planetary science, think of tectonics as the planet's way of stretching and releasing built-up stress, much like a slow-motion earthquake system that shapes mountains, volcanoes, and even atmospheres over billions of years. This exciting revelation stems from cutting-edge computer models that simulate how a planet's outer layer, or lithosphere, bends and heats up under various scenarios. Researchers spotted this overlooked pattern, calling it the episodic-squishy lid, which captures how some worlds flip between calm stretches and bursts of activity. Picture it like a rubber band. Sometimes it's rigid and unmoving, other times it softens just enough to snap into motion, releasing energy in unpredictable waves. This isn't your textbook plate tectonics. It's a more flexible, intermittent style that could explain why our blue marble Earth buzzed with geological drama, while its twin Venus sits trapped in a hot, lifeless hush. And here's where it gets controversial. Does this mean Venus was once more like Earth, but a fateful switch locked it into stagnation? Some experts argue it highlights how tiny differences in cooling rates or internal heat could doom a planet to barrenness, sparking debates on whether we've overlooked similar what-ifs in our own solar system. To break it down simply, traditional views split planetary behaviors into two camps: the mobile plate tectonics seen on today's Earth, where chunks of crust slide around like puzzle pieces, driving earthquakes and ocean creation, or the stagnant lid on places like Mars, where the surface stays locked in place, letting heat build up without much release. The new episodic-squishy lid slots in as a hybrid, involving cycles of quiet followed by intense episodes fueled by magma intrusions from below and chunks of crust peeling away, in a process called delamination. Imagine peeling an onion layer that temporarily makes the whole shell more pliable before it hardens again. For those new to this, delamination is like the planet shedding heavy, dense lower crust to lighten up, allowing more movement. It's not constant chaos, but rhythmic pulses that might have kick-started Earth's full tectonic engine as it cooled from its fiery youth. This on-off rhythm could be the missing link in our planet's history, gradually toughening its outer shell for the vigorous plate action we see now, complete with recycling of surface materials back into the mantle. Delving deeper, this discovery also unravels the memory effect in planetary history, the notion that a world's past geological habits influence its future paths, making shifts between these modes more foreseeable as things cool down. By charting all 6 possible tectonic styles for the first time under varying conditions, the team created a roadmap of how planets evolve, showing smoother transitions once the lithosphere starts to weaken, just as Earth's did eons ago. Study co-author Guochun Zhao from the Chinese Academy of Sciences points out that ancient rocks on our planet match this squishy-lid pattern, with cooling making the crust crack-prone under targeted stresses, paving the way to modern tectonics, and crucially, habitability through cycles that nurture water and atmospheres. But this is the part most people miss. While it celebrates Earth's journey to life-friendliness, it raises tough questions about Venus. Same size, similar start, yet no plates in sight, just volcanic scars, and weird ring-like coronae from resurfacing events. The models mimic this by simulating an episodic, or magma-heavy squishy-lid state, where deep plumes and melt weaken the lid sporadically without birthing true drifting plates, tying Earth's ancient vibes to Venus's present in one cohesive story. Co-author Maxim Balmer from University College London emphasizes how these simulations connect deep mantle flows with surface eruptions, offering a single lens to view both planets' timelines and hunt for Earth-like twins among super-Earth exoplanets. Since tectonics control the dance of water and carbon between a planet's guts and skies, think how subduction on Earth pulls ocean floors down to regulate climate. This regime-shifting insight could pinpoint worlds with balanced environments ripe for life, steering telescopes and probes toward promising targets. For example, on a beginner level, imagine scouting exoplanets. Instead of just size or distance from their star, we'd check for signs of this squishy flicker, like intermittent quakes or volcanic glows, to gauge if they cycle elements effectively for stable oceans or breathable air. Published on November 24 in Nature Communications, this work isn't just academic, it's a game-changer for astrobiology, blending Earth's vibrant past with Venus's enigmas to broaden our cosmic neighborhood search. So, what do you think? Could this episodic lid be the key to spotting alien Earths? Or does it overcomplicate the hunt for life? Share your take in the comments. I'd love to hear if you agree it's a breakthrough, or if Venus's story makes you question habitability rules altogether.